Mr. Bergman said, my name is McDaniel. I serve as the country manager of NuScale Power in India for just over 1 year now. NuScale Power is a venture capital funded small modular reactor company, the first and leading of the variety of the small modular reactors. And I'm going to talk to you a little bit today about our reactor, about what we're looking to do in India, and most importantly, I'm going to focus on the discussion of safety, because this has become a very important issue that NuScale has had in mind since the inception of the company. I'm realizing the lights get dimmed every once in a while, and it might be a little bit hard for everybody to keep their energy going. So at this point, I just wanted to excite the other hat I wear is with the American Nuclear Society India section. I wanted to make sure, raise your hand if you have already picked up your gift bag. Okay, most of you still need to get your gift bags. They're either going to bring some over here or you can get them up there. You want to get your gift bag. So those of you who grabbed your gift bag, how many of you have looked inside and seen the gifts? Okay, well then the next part's not going to work. I was going to ask if any expat or first-time visitor to India looked in their gift bag and saw the gift from NuScale Power and knew what that gift was. I see one expat up here who's looking through his bag. And again, this stick is not going to work because nobody's actually looked at their bag. I thought that's what everybody did when they got a gift bag. So in the gift bag is a small modular reactor. If you look at, does anybody have to pull it out and show it? Don't worry, I'm still going to keep under 30 minutes. It's just wanted to get people a little bit more engaged here. Come on, Stuart. It's right there. It's orange, the NuScale color. So I'll just go ahead and tell you. So, no, not Bechtel. That's a patty cake. Okay. So, Ben, do you know what that is? A candle. You know what kind of candle it is? I mean, it's small. You can move it from place to place, so it's modular. And it's a candle, so it's a reactor. It generates heat. But do any of the expats, don't make me ask the ambassador or the principal deputy assistant secretary to explain what it is, but what kind of a candle is it? All right, you guys are absolutely too tired for this presentation. I've got to get you going. It's a Diwali candle, and Diwali is going to be happening later on this month, and so we thought we'd give those candles out, and it might be the first time that you go to a nuclear conference and get a Diwali candle. So I won't explain the golf balls that are in there from McDaniel Technical Associates, but hopefully that gives you something to look at while I'm giving my presentation. So as I get into my presentation, I do have 2 of the videos. I'm going to turn the volume up really loud to keep people awake, keep people going. And I might just strategically play those whenever it looks like I see somebody in one of the last aisles maybe falling asleep. So I'm going to jump in. I do have 42 slides, but I said there's only 6 I'm going to really focus on. Some of them I'm going to go by very quickly, but the entire presentation will be put on the American Nuclear Society India section website. Hopefully some of the other presentations could be up there as well if you need to look at those for reference at a later time. So who is NuScale Power? NuScale Power, as I mentioned, venture capital funded company, small modular reactor. We feel that we've changed the game for nuclear by designing a commercially viable, modular, scalable nuclear power reactor. When we say modular, we mean that the entire reactor can be factory manufactured and delivered on site, ready to be fueled and operated. When we say scalable, the modules, each module will be 45 megawatts electric, 160 thermal. Each of those modules will be delivered to the site, and our standard design, because you can't submit a license application for any number of reactors. Our standard design is a reactor site that would house 12 reactor modules. After we license 12, our next plan is to license 6, but there's any variety of size. As we're going through the regulatory process, we are the first of the small modular, the first truly scalable reactor. So we're going to be breaking ground in that as we go through the licensing process in the United States. And commercially viable, I'll talk about some of the reasons that we think it is commercially viable, and that others, we've gotten a lot of attention last year. I won't mention all of the attention that we've gotten, but I will just jump to one point, and that is that as a venture capital funded company, we keep going by finding strategic partners. And we are happy to be able to just announce that we do have a strategic partner that we're in negotiations with. It is not complete, but we think that this agreement, there's no reason why an agreement can't be reached, but we're working with the Fluor Corporation, one of the largest EPC companies in the United States. And that company who's built nuclear reactors in the United States has provided bridge funding already to the company. We're hoping they will be able to make a much larger investment. And I would just say, look in the news and keep looking for NuScale, and you might hopefully see something in the near future. That's what we're hoping for. Again, we've been featured in a number of, Green Tech ranked us the #1 new green technology in 2010. In 2009, there was a nice piece in the New York Times. And Secretary Chu, the U.S. Department of Energy Secretary, has become a big fan of the small modular reactor. And I will read his quote. Well, okay, I'll read one part, where it says, countries such as China, South Korea, and India have recognized and are making investments in nuclear power. And the choice is clear: develop these technologies today or import them tomorrow. NuScale is a 100% U.S.-owned company with 150 U.S. employees currently. We intend to manufacture and construct the first reactors in the United States, but then we look to export those reactors, and we will be open for strategic partnerships for not only the supply of the components to the reactors when we export the reactors, but also utility partners that can help market and develop the reactors in these countries. Two people I'll mention because they're the highest two and they write my checks, but the NuScale team, our CEO is he's a PhD nuclear engineer and has a law degree. He's been a utility executive, and he was the first PhD graduate of the Oregon State University, which I'll discuss a little bit more here in a second. Dr. Jose Reyes is the Chief Technology Officer. He is really the author of the NuScale reactor. He'd previously been at the IAEA as the technical expert on passive safety systems. He'd also worked with the U.S. Nuclear Regulatory Commission, and he is currently, I think, on leave, but he's the department chair of the Oregon State University Department of Nuclear Engineering, which is the university that developed this technology. I think there's a slide on the history, but just briefly, the history of the NuScale reactor is that Oregon State University, because of Dr. Reyes, bid to produce a study on the multi-application small light water reactor program that the IAEA bid out, and the U.S. Department of Energy awarded Oregon State University with partners Bechtel and the Idaho National Laboratory to develop a small reactor for application in developing countries. The result of that reactor, Oregon State developed a test facility, which I'll show here in a second, and that test facility is a one-third scale mock-up of the NuScale reactor. The university itself then spun off NuScale as a private venture in 2007, and that venture is the company that we have today, which is known as NuScale. The rest of our executives are technical experts. Ed Wallace was the head of the PBMR program in South Africa, which is not advancing right now, but he's now with us handling our regulatory issues. We've got folks from Los Alamos and just a really great team in the United States of some of the best experts in the world, we think. So the theme of my discussion today is that, nuclear power will continue post-Fukushima. You heard that yesterday. You heard it from Dr. Banerjee. You've heard it from Dr. Sinha in India. You've heard it from the other people up here talking about the large reactors. The small reactors, we think NuScale is poised to lead. We were the leader in the first place, and now there's been several entrants into small modular reactors. We think we still have an advantage having moved first and fastest. So 4 of the principles of our reactor. The first is economies of small, which is obviously the opposite of economies of scale. You build one big 1,000 megawatt or 1,500 megawatt reactor. Some of your systems, you're going to save some money on those, but you're also going to have some very robust systems. Our reactor goes the opposite direction. It goes small. Think of taking a typical core of a 1,000 megawatt reactor and dividing it by 20, and you've now got smaller reactors. You can purchase fewer of them, which might be easier if the financing is an issue. Our estimated costs for a 540 megawatt reactor site, which would include 12 modules, 45 megawatts each, would be on the order of about $3 billion. We've done an extensive cost estimate. If you're interested in purchasing, we are selling them at the counter at the NuScale booth over here, just right as you walk out. So we are taking orders. Just let me know. The inherent safety, which is what I'm going to focus on in the last 6 slides, and is the focus of my presentation today. I'll talk about that. And then the siting flexibility, and this has been one of the #1 issues that has been brought up in India. People are always asking, how big is a site for a small modular reactor in India? Well, the answer is our sites are 16 hectares, or 400 by 400 meters, which is about 40 acres, which is a very small site if you know the size. I don't know the exact numbers of what the sizes are for the larger reactors, but it's a smaller site. And particularly in India, land is going to be a big issue. I'm going to talk about the seismic design a little later and the scalability. And I don't think we have to talk about the advantages of nuclear over other sources in terms of climate change, or that in the United States we have 1,112 coal plants, and many of those are being retired, and there's going to be new need for new baseload in the United States. Obviously, India has even greater demands. And this is a slide that illustrates the retiring nuclear capacity that is going to be a big concern as some reactors get retired. So why small modular reactors? The primary interest until February of this year in small modular reactors was primarily financial. And one of the biggest reasons is because it's a $3 billion price tag, not a perhaps $10 or $15 billion price tag. And so the number of utilities or potential customers grows, and the number of potential communities that might use this technology is wider. So we're not necessarily looking to build 100 of these for Maharashtra, for Mumbai, although we would if we were asked. But we could, build smaller reactors and smaller size, and you could buy 6 of the modules, which would be 270 megawatts, and have all the infrastructure in place. And then as your demand grows, you could add another 6 modules and be 540 megawatts. 2 plants, that's 1,000 megawatts. So these are just some of the recent quotes since Fukushima about the interest in small modular reactors. Everybody was impacted by Fukushima in the nuclear industry. Some countries that were already probably not going to build have announced they won't build. Some countries, like India, have proclaimed that they will still build. And what we found at NuScale is, it could have gone either way. It could have been, we're no longer interested, nobody will ever invest in a company, a small modular reactor company, or somebody might invest. And what we've seen is we had a large amount of interest, and we do hope that we're going to be able to secure financing of a U.S. engineering company. That company will then help us probably identify our supply partner for the other components. And we already have a board of about 11 utilities in the United States that we're in discussions with for purchasing the reactors. U.S. Department of Energy may not be as interesting to India, but just to give you a perspective on the United States, the U.S. Department of Energy does have a program proposed, a 5-year program, to commercialize 2 designs of a small modular reactor. We have received support in both the House of Representatives and the United States Senate. We're currently in an appropriations process right now, and because I don't have 2.5 or 3 more hours, I won't go into that process. But I will say that we feel really good that potential teams that would be getting NuScale is partnered with Mid-American, a utility owned by Warren Buffett, a very large utility in Iowa, would be the potential site. We're also partnered with the Savannah River site, the Sandia National Laboratory, White Sands, and Energy Northwest is another utility. Generation Empower, who has displays here, is a partnership of Bechtel and Babcock and Wilcox. They're also looking at this, working with Oak Ridge National Laboratory and the Tennessee Valley Authority Utility. And Westinghouse Holtec, also participants in the U.S. Pavilion, have designs for small modular reactors. This is our utility board. You may not recognize many of them if you're in India, but like I said, Mid-American, owned by Warren Buffett, who you may have heard of. But the other utilities, Entergy, Exelon, the 2 largest nuclear utilities in the United States, all of these companies have been on our advisory board for nearly 4 years now, looking at purchasing these reactors in the United States. So the design, I mentioned, we have a 1/3 scale operating test facility that was built based on the 2000 award of the contract for the multi-application small light water reactor. But back in 1994, Oregon State University, Dr. Jose Reyes worked with Westinghouse, the AP600, AP1000 to develop the thermal hydraulic simulation that allowed that reactor to be licensed and to be without having to build a prototype. So based on that experience, Oregon State, that's the reason Oregon State won the contract to do the, at the beginning of the process, you go through everything that you're going to submit was reviewed by Mr. Bergman of the U.S. Nuclear Regulatory Commission. And we discussed that. We've had several discussions. We have a docket online where you can view the discussions that we've had about our reactors. Everything we submit will be discussed at least a couple times before it's submitted, and then it will be discussed many times after it's submitted. Optimistically, we can hope for about a 3-year approval process. If that were to happen, then 2015 might be the year that we would be able to start operating our reactor. We'll apply for a license, a combined operating license for our site and our design certification at the same time. And then it would take about 3 years for us to construct the reactor, or to construct the park and actually the reactors and have those operating. So the earliest date would be 2018. In India, that would probably lag by at least 3 years as we would go through the U.S. process, and once we are qualified and licensed in the U.S., then we would apply for the same in India. And we're developing that path forward right now. And India does not have a small modular reactor market right now, but NuScale is hoping to open that. So this is, I've got some videos. I'm not going to bore you with, again, talking through each of these things and giving you the slides as much as I'd like to feature a video. And what I'll do is do that right now because I saw a couple people nodding off a second ago. So, and I'll turn the volume up really loud too. Usually we don't do the volume because the graphic design team gets a little overambitious. There we go. With the sound. So this is the NuScale reactor. This is the core of the reactor in red. This is about 1/20th the size of a larger LWR. However, it uses the same standard, less than 5% enriched fuel, typically a Westinghouse standard PWR fuel, 17 by 7 or 17 by 17, and it's half the height of the normal fuel. What you see happening here is the reactor heating up, and the water is entirely being circulated with natural circulation. The hot water rises as the water comes around the top. It goes around back in the reactor and comes back through the bottom. There are no pumps in the reactor in the primary loop. The heat exchangers are integrated heat exchangers inside the vessel itself, and the heat exchangers have a hot loop, cold loop coming out, and just like any other reactor, we go to a turbine. Each of the 12 modules has its own dedicated 45 megawatt turbine, where the electricity is generated in the turbine, the water is cooled, and we would primarily use a normal condenser and water cooled, but we've looked at this can certainly be done with air cooling. You lose a very large factor, but in some places if you don't have enough water, you could use air cooling and still have the reactor operate with a loss of efficiency that could neighbor maybe 30 to 40%. It would vary by the case and the ambient conditions. So this just shows the using the water to cool the reactor. Obviously, if you had a 540 megawatt reactor, you would use half as much water to cool it as a 1,000 megawatt reactor. So there may be some areas in India that would be more applicable inland that we wouldn't necessarily have to be on an ocean for cooling. And this is the water returning to the reactor from the steam generator. And again, the steam generator, this is a PWR. The steam is generated right there in the really red part. Don't worry, I've got one more video. Uh-oh, now I have to figure out which presentation I was getting. Hold on. Okay, that's the one. And now I have to do this. So a quick video of the technology, but it is actually that simple. The fuel at the bottom, the integrated heat exchanger, and the water naturally circulating throughout the reactor vessel. The size of the reactor is The reason that it's 45 megawatts is actually a back calculation of what is the largest size of reactor vessel that you can build and still put on a truck or a barge or rail and still ship it. And that's where we came up. This design it's a 400-ton reactor without obviously no fuel. The fuel is done after the reactor reaches the site, but this can actually be delivered. I don't know if all the roads in India can handle this, but certainly some of them could. And this is a side view. Each reactor has its own steam turbine generator, so when one reactor is being refueled, and our refueling is again, typical of the larger light water reactors. Just looking at my time, and now I'm going to go much faster. This is a side view of the reactor with 6 of the vessels on one side. This is our spent fuel and the fueling on the right-hand side. This is where I would show you the refueling video if I have enough time at the end. This is our GSI simulator, which we're currently working on with the U.S. Nuclear Regulatory Commission to have an operator operate up to 4 reactors at one time. And so you'd have 3 operators operating 4 reactors for a 12-reactor site. And this is a picture of the site. The very middle section are the reactors. The turbine generators are on the outside, and the evaporative coolers are on the outside of that. I mentioned 540 megawatt would be a 12-unit plant. And this is from our cost estimate. We estimate that our cost will be comparable to the larger reactors, but again, perhaps easier to finance because of the larger overall cost. Discuss the economies of small, and I'll skip to talking about the safety case for NuScale in the post-Fukushima world. Again, checking my time, I'll focus about a minute on each of these last 6 slides because these are the most important one, and this is the reason that we're here today, to talk about the safety advantages of these new reactors. So I mentioned it's natural convection for the cooling, which requires no pumps, no emergency generators. We have the design is seismically robust. The modules themselves sit in a pool of water, which provides an extra level of seismic dampening, which attenuates the ground motion. Each reactor is 1/20th the size, so if you have 12 of them, it's 12/20ths the size of a larger reactor, 1,000 megawatt reactor. And then defense in depth, which is the next slide. But again, our stainless steel containment is 10 times stronger per megawatt than a PWR. And the water volume inside our vessel is 4 times larger than, resulting in better cooling. And again, we only have 5% of the fuel. I've said that before. So this is our seismic design that we've looked at 0.5 G, which I don't know the latest number from Fukushima, but I've seen numbers of 0.53 and I've seen numbers less. Does anybody know what the number was? What we estimated as the Fukushima? So we were very excited to have a 0.5 seismic limit for the reactor or seismic test with 5% dampening. But as Gary points out, Fukushima may have been 0.6, so that actually would still probably be an out of design basis accident. But we've completed a probabilistic risk assessment preliminary PRA that has us on the order of 10 to the minus 8 due to the barriers, which I'll discuss right here. So, like in a reactor, we have our fuel pellets are off-the-shelf cladding. The reactor vessel that we have, like other reactor vessels, ours is, we think, going to be sufficient. Then there's the containment that surrounds the reactor vessel and a vacuum in between. But then in addition to that, there's the cladding, there's the reactor vessel. There's the containment. Around that, we have a pool of 4 million gallons of water that surrounds the reactor. Around each reactor, we have, that's me telling myself I have 5 minutes left. Around that, we have a lined steel concrete reactor pool and shielding between each reactor, a biological shield, and then the reactor building itself. Get through all of those. So the other presentations talked about, they have the videos of loss of coolant accidents. We're actually producing that video right now, but this is a slow motion slide version of 1 second after the reactor is scrammed, we would be down to 10 megawatt thermal, similar to the other designs. At around 1 hour, we'd be down to 2.2 megawatt, one day, 1 megawatt. And you see the reactor at some point, so 3 days, if boiling is occurring, the water that is surrounding the reactor, we estimate we'd have 30 days of water similar, well, I won't say anything similar to Fukushima, but I'd say if we have water surrounding the reactor, the water can come into the reactor for up to 30 days of cooling. After 30 days, it would be air-cooled indefinitely. So again, we talk about the U.S. requirement is 72 days of passive cooling without power. We believe that our reactor will operate indefinitely without power, because there are no pumps in the reactor. It would be natural circulation. We think for 30 days of water, to get it down to 0.4 megawatt thermal, would allow it to then operate indefinitely with the air cooling. And our spent fuel, this is our spent fuel pool, and I do want to show the video. All this will be available online, but we've taken a lot of the lessons of Fukushima and discussed these, and we think that because our reactor is below grade, has larger volumes of water by design, our pool liners and a seismically robust design, we think that a lot of the instances that we would be worried about with Fukushima, that our reactor would perform very well. So again, we don't expect any major impact on our design as anticipated. We're going through the process. We'll make designs as we go through the regulatory process in the United States. As a result of Fukushima, we've added our long-term air cooling tests. So we're now simulating our reactor to verify what we think would happen on the air cooling scenario. We're reviewing our spent fuel pool capacity, both the tight and, I'm forgetting the term. So different types of ways that we can bundle the fuel, or have the fuel bundles, so that in a case of Fukushima, that those may also be air cooled. So that is the conclusion of the presentation. And with my remaining 3 minutes, I'm going to show you our graphic, and I'll turn the volume up to keep everybody awake. Sounds are going to be a little bit cheesy. I'm just warning you, but this is to keep everybody awake. So 4 steps. This is the coming through the NuScale reactor. So we don't have the GE budget to hire the professional speaker, so you're just going to have to listen to me come up. Just pretend like this is on the audio. So this is the reactor building. See the side profile to the right is where the 6 modules on one side would go, 6 on the other side. We're going to show when the reactor vessel shows up, fully assembled. First, the lower vessel comes in the reactor. You can see the little person standing there to get a perspective on how big the reactor is. And sorry I can't make this go a little bit faster. But, I swear I'll stay right to about my 30 minutes. So this is the lower vessel coming in. Then next we're going to put the fuel in, and I may just skip a little bit to make it go a little bit faster. Okay, so that's now the lower containment vessel. Again, all of these parts are going to be manufactured. The first components will all be manufactured primarily in the United States. But we are looking for partners. Obviously, not every part will come from the U.S. But as we're looking at partners, we'll be looking for partners to supply reactor vessels, larger components, longer term, especially if we are able to enter the Indian market and produce a lot of these modules. But in the near term, we're talking with everybody who's interested in talking about prospects for putting together our supply chain. We'll likely have one or two primary supply partners for the larger components, but everything else. I live here in Mumbai, so you get my business card, which is in the next to the Diwali candle. Please feel free to contact me. So this is the fuel being taken out of the fuel pool and inserted into the lower vessel. It's not letting me move the mouse. Okay, and then we assemble the module. So the analogy we use most often is a thermos bottle. Turn it upside down, open up the thermos bottle, put the fuel in, tighten the thermos bottle. We don't screw it, we fasten it. But then the thermos bottle with the fuel in it, with the two barriers, is put into place. I'm sorry, I'm talking faster than the video. So I'll just click record that. Come together, pick up the fuel, take the lower vessel, and voila. You have a 45 megawatt electric NuScale module, passively safe, and very slowly. Believe me, in real life we actually do it even slower than this, so that's the point of maybe the video going so slow. And with that, I conclude. Thank you.